All right, so the next two slides that I have for you can be a little bit tricky for some people. All right, so I want you to pay attention. If you are struggling with this or you're scratching your head and you just want to make sure that you understand it, please send me an email. Actually, send me an email anytime things are a little muddy or fuzzy or like you're, what the heck? I don't get this. I do want to hear from you. But I know that this is sort of one of those places in the semester that people are just not totally groovy with. So this is latent heat. The little trick I play with myself is I think of latent heat, I think of Lay's potato chips. Latent Lay's. I don't know why it works for me, but it does. I think latent heat, potato chips. Potato chips are couch potatoes. You're sitting on the couch and you're eating a lot of stuff, and what's happening? You're not using that energy, you are storing it. All right, so you are a couch potato. You are storing energy, you are not using it. That's what latent heat is. It's the amount of energy stored. Latent heat is really critical for the environment and for our planet because it accounts for 30% right here of the amount of energy transferred in the atmosphere. All right, that's a really significant amount. And that latent heat is primarily transferred and generated through the water molecule. Now, the water molecule is made up of hydrogen bonds, and we had said at one point that solar energy comes in and those hydrogen bonds just don't break. They absorb and absorb and absorb a lot of energy. And because they're taking in a lot of energy, they're going to release it really slowly as well. All right. And so they're big storage units of energy. Because our planet has lots and lots of water, we have lots of storage capacity of energy, and it's the best battery that we've got. We can keep that energy in the Pacific Ocean, in the Gulf of Mexico, in the Sea of Cortez for long periods of time, and then it gets re-released when we need it the most, which is in our winter months. So water is really important in terms of latent heat. So what happens is it moves through the atmosphere with phase changes. Water can exist in three phases, as I know you all know: solid, liquid, and a vapor. And these phase changes are either the water is melting or it's freezing. It's either evaporating or it's condensing, or one that some of you may not have heard of, which is it's sublimating. It's a sublimation where it goes right from a solid to a gas. There is no going from a gas straight to a solid. All right, but sublimation, a solid to a gas, does occur. Those will occur in laboratories, but on planet Earth, it happens at the margins of glaciers, where newly exposed Earth, it gets really hot. It's dark in surface. It has a low albedo. The temperatures get really high, and then the toe, the edge of the glacier, whoop, just vaporizes. Pretty crazy cool thing to happen. All right, but it's pretty small in volume, you can imagine. All right, so with phase changes and the driving of the atmosphere with latent heat, what we get is pretty much an absence of energy when we have a solid. And that solid over time is going to start to absorb energy, solar energy. Think of a lake. And the top of that lake is solid, and it's going to take a long time for it to receive enough energy before it begins to melt. And so on this graph, I have time here, how much time it takes. So I have a solid object for quite a bit of time, and then it starts to melt over a large period of time. Now, note here that the temperature is increasing until we get to 0 degrees Celsius, 32 degrees Fahrenheit, and we have time going on where melting is taking place over time, but the temperature, note the temperature did not change. We're not increasing in temperature during this phase change. All right. And then once we have liquid water, At 0 degrees Celsius, it is now a liquid and it can start to increase in temperature until it's about 100 degrees Celsius, 270 degrees Fahrenheit, and it's going to start to evaporate. But the temperature again doesn't change. We're increasing and we're adding calories and we're adding energy and we're adding energy and adding energy, but we are not increasing the temperature. We are initiating phase change. And when we have enough calories, enough energy in that water molecule with those hydrogen bonds, then we phase change into gas and the temperature goes up again. All right. So that's one direction. The other direction is now we cool off the gas and we lose enough energy and enough calories to then it's condensing into water. And it condenses and it's 100 degrees Celsius, 270 degrees Fahrenheit until we've lost enough energy, and then it becomes a liquid. And then we can then lose energy and lose temperature. And this is a 1-to-1 ratio when we measure this in Celsius. For every 1 degree Celsius, we lose 1 calorie of energy, or 1 degree. So it's a 1-to-1 ratio. And until we've lost enough energy, then we start to freeze that water. And we freeze that water at 0 degrees Celsius, 32 degrees Fahrenheit, no change in temperature, and we can have solid 0 degrees, 32 degrees, 32 degrees Fahrenheit solid, or we can have 32 degrees temperature water. Here we can have 100 degrees Celsius liquid or 100 degrees Celsius water vapor. All right. So this is what a phase change is. We are adding we are adding energy to the atmosphere when we are freezing water, when we are condensing water. We are taking energy out of the atmosphere and putting it into the water molecule when we are melting that water and when we are evaporating that water. All right, so on melting and evaporating, energy is going into the water molecule. On condensation and freezing, the energy is going back into the atmosphere. So consequently, with sublimation, we're going from a solid to a gas. So we're putting energy into the water molecule with that. All right, next slide. So the math works great for Celsius, so we're going to do this in Celsius. It gets a little funky with Fahrenheit. All right, this is a nice 1-to-1 ratio. So the principle is if you have 1 gram of water at 0 degrees Celsius, it's going to take 80 calories of energy to make it water. So I'm going to add 1 calorie, 2 calorie, 3 calorie, 4 calorie, all the way to 79 calories of energy. I'm still going to have ice. When I add 1 more calorie and make it 80 calories, I have liquid water. But look at this. I have 0 degrees Celsius water, 0 degrees Celsius water. One is liquid, one is solid. I've changed the phase, but I have not changed the temperature. What I changed is the addition of 80 calories. So far, so good, I hope. All right, this is where the math is best. So I've got 0 degrees Celsius water. I'm going to add 1 calorie. It's going to go up 1 degree Celsius. I'm going to add 5 calories. My water is going to be 5 degrees Celsius. I add 30 calories. It's going to be 30 degrees Celsius. I add 99 calories. It's going to be 99 degrees Celsius. All right, I add 1 more calorie at 100 degrees. And now I have 100 degrees warm water. Hot water, actually, right? That's pretty hot water. So we're going to phase change this. I'm going to add 1 more calorie. And I'm going to have really hot water. I have to add 540 calories to make it vapor. Again, the temperature didn't change. I have 100 degrees Celsius water here as a vapor. I have 100 degrees Celsius here as water. No temperature change, but I have a phase change because I've added a whole lot of calories. 540. It takes a lot of energy to break the attraction with the water so you have liberated molecules as a gas form. All right. In order to so this is how we're going to lift water into the atmosphere. So on the surface of our lake down here, the lake might be pretty cool, but every little molecule is going to warm up enough, have enough energy, so it's going to lift. So it's going to be vapor, vapor, vapor all the way through here. And remember our adiabatic lifting. As we're lifting, we're cooling, which means we're coming through here and we're losing these 540 calories as we're lifting. So we've got our maximum amount of calories. If you want to do the math, it's 540 plus 100, so we're now at 640. And then we add another 80 to a total amount of 720 calories. So we have 720 calories with a molecule of water here, which has said, I have enough energy, whoop, I can now lift into the atmosphere, and as I'm lifting, I'm losing those calories. I get to an elevation where I have lost 540 calories, so I start to condense out and I become liquid water, which then forms a cloud. Not so bad, huh guys? So this cloud is anywhere between 100 degrees Celsius and 0 degrees Celsius, or it can start to cool even more, and we can start to generate snow and ice in here as well. So depending on the temperature that we have here, which is going to result in how many calories we have, we're going to then precipitate out rain or snow or sleet or hail, and transfer that energy. So on this case, now we're going to then release energy back into the atmosphere. So as we're lifting, we're putting 540 calories back into the atmosphere between the base of the cloud and the surface of the water. If this cloud continues to cool, if the molecules continue to rise in this cloud, we're going to continue to lose calories, and we could lose another 100 calories to the atmosphere out here. So we're regenerating the atmosphere, everybody. All right. And then, of course, if we get a solid, then we've lost all of that energy and it's falling as snow or sleet. So, but all that energy is infused back into the atmosphere at this point. Now, a favorite story of mine is how much energy is 30%. And Hurricane Katrina was a long time for everybody. I was a grad student in Texas at that time. And at the moment that Hurricane Katrina hit the Gulf Coast, hit New Orleans, not as it was approaching the shoreline, not as it sat on the shoreline, not as it was penetrating into the state of New Orleans, Louisiana. Sorry, almost forgot my political geography there. As it was moving into Louisiana, but just at the very moment that it hit, there was enough energy being released onto New Orleans to light every light bulb in Broadway, every hairdryer, every honking horn, every cappuccino maker. Broadway has enough energy in that moment of time for 7 years. That's how much latent heat energy it was dispelled in the moment it hit the shoreline. Now, It hit the shoreline and then it moved inland and then it moved further inland and it moved further inland, and it's losing energy as it's moving inland, but it's still got an enormous amount of energy. So when you think about, we're more than a decade out, we're starting to approach 2 decades actually, 15 years out from Hurricane Katrina, and what we've got is still recovery efforts. We still haven't recovered fully from all the damage because of the vast amount of energy that that storm hit the coastline with. So we've got other storms more recent in memory for you. We can think of Hurricane Sandy on the East Coast, and the series of hurricanes that we had just last year as well that were damaging. So lots of power in latent heat. All right, guys, so no wonder we're driving the atmosphere and creating storms globally, because we're putting a lot of energy into the atmosphere from evaporated water. Okay, on to some next